Alright, silly people, here's the situation. We're going to be calculating this integral, which is the sine squared of the square root of 100x dx, using first the adaptive trapezoidal rule method, and then also after that the Romberg integration method. So let's just do the adaptive trapezoidal rule before we start getting crazy. I see that there's a sine function in the integrand, so I know I'm going to import numpy as np, and then define the integrand as a function f of x. So that's going to return the sine of the square root of 100 times x, and then you square the sine function, right? Okay. Okay. The adaptive trapezoidal rule method, you start out with a n equals 1 calculation of the trapezoidal rule integral of this, and then you put it in a loop and you double n, and your answers are actually dependent on the last value that you get. So starting with n equals 1, a equals 0, b equals 1, h equals b minus a over n, s equals 0.5 times f of a plus 0.5 times f of b, and then you do your 4k in range 1n, and then go all the way to s plus equals f of a plus k times h, and then you just do I equals s times h, right? That's the whole trapezoidal rule method in a nutshell. We just did n equals 1 for this guy. So what I'm actually going to do is I'm going to call this integral I underscore old, because we're going to iterate through different integrals, which I'm going to call I in reference to this to calculate an error. So right now, I'm going to make the error just an arbitrary large number. I'm going to make it Avogadro's number, in fact. And we're going to start a while loop. So while e, or actually the absolute value of e, is greater than our desired accuracy, which is 1 e to the minus 6, then we have to do this thing where we take our, we have a new integral called I, and actually at this point let's make n equal to 2 for the first iteration in the loop, right? You take I equals I underscore old, and then you introduce a loop. So 4k in range 1 to n again, and then you do f of I plus equals h, and you do have to calculate a new h. So h is now b minus a over n, and actually you divide your old integral by 2. Clever distinction. But then you do I plus equals h times, it's just going to be f of a plus k times h from before, but only for the odd values of k, which is a clever distinction there. So only if k mod 2 is not equal to 0 should you add on h times f. Right. Okay. And then afterwards, you have your new value for the integral. You can calculate what the error is on that. So e will be determined by just, if you take whatever value you have for your current integral, subtract your old integral, and divide by 3. And then you, to iterate to the next step, multiply n by 2. So So, and then also make your new integral the new old integral to keep on calculating the error as you go. And then the program did want a print statement, so let me go ahead and print the value of the integral. So I equals, comma I, the error. So error equals, let's put a semicolon here for readability, E, and then in here, semicolon, n equals n, and they'll see if that runs. I happen to know that the value of the integral should be around 0.45, and it got there after several steps. But yeah, that's the adaptive trapezoidal rule method. It was still going to end up being kind of slow compared to the next integration method that we're going to do, which is the Romberg integration technique, which is pretty confusing the way that's like talked about in the book, let's be honest. But for fun, right now, I'm going to take this bit of the code here, I think, to do the next step. That's just the importing numpy, setting the initial value of n, and then getting initial value for h, which I don't think we even really need. So Romberg integration is based on making an array of r values where the length of the row matches whatever row you're on. So let's go ahead and get an array. I think that the size of this won't have to like exceed 10, but I'm going to go ahead and make the thing something that you can change. So I'm going to set the size to 10 and then define the array R as numpy zeros array of size, comma, size with the data type of floats, right? So we're still going to have a while loop over values for the error, so I'm still going to do while absolute value of E is less than 1E minus 6, and then manually set E to 6.02 e to the 23 first of all, so it starts off really big and will get smaller as we go. The first element of each of the rows is just the result of the regular trapezoidal rule method. So we also have to have a variable that is going to be called I. This is going to be used to index the R array, but then this is just going to end up being, again, the trapezoidal rule. So we do H equals B minus A over N, and then you do just that S is equal to 0.5 times F of A plus 0.5 times F of B. And you do 4k in range 1 to n, and then S plus equals F of A plus k times H. And then you make it so that the first element of your first row of the Romberg array is equal to H times S, the result of the trapezoidal rule integral, right? Now you can iterate over values of m. You want to do 4m in the range. You want to start with 1. You don't want the 0 with m. That's going to make things weird. And then you want to run until m equals I, whatever your row you're on. So I'm going to do I plus 1 here. And this is going to explicitly calculate the element R of sub I m. Now, I mentioned that the way that old Newman presents this part of the problem is really weird. And in fact, I don't even think that it's correct, because he does a formula which solves for r sub I comma m plus 1, which is confusing in itself if you're trying to write code. But so I'm just going to instead write out what it would be if it was r sub I comma m, which that ends up being r sub I comma m minus 1 plus, and then there's a fraction here, 1 over 4 to the m, not 8, m, minus 1, and then multiplied by these things in parentheses, which end up being r sub, and it's capital R, I comma m, minus r sub I minus 1 comma m minus 1. Right? And that's, again, it's the same formula. It's just taking all the places where m shows up on the right hand side and subtracting it by 1. And I think you even have to do, this guy has to be minus 1 as well. Yeah, so that's the formula that I'm going to use. It's not the same as what's in the book. Just wanted to make it clear. So now you do r sub I m minus 1 plus, and then instead of putting the fraction out front, I'm going to put it behind. So in parentheses r indexed I m minus 1 minus r indexed I minus 1 m minus 1. And then you divide by 4 raised to the m minus 1. Right. Afterwards, you can calculate the error on whatever index you're on, and you should even put it in this for loop so it does it for each m. But then the error just ends up being this part of the integral here, just that whole bit. After that, you multiply n by 2, and you iterate I up by 1 to continue the thing, and then just as a trial, let's go ahead and print out what r is. That is not right. Oh, I still need to flip this alligator. Okay, now this is looking good. So it didn't even need to be 10 by 10. It got to the correct answer, and that looks like 7 steps. 1, 2, 3, 4, 5, 6, 7. Yeah. So that's pretty nice. And then if we wanted to print it out in a nicer way, then what is that? More akin to what is in the book. You can put it different for loops. So for I in range size, let's just kind of check every row. If the row does not start with a 0, then we can print out the whole row. So star r I comma colon, but index only the ones where it's not, so not equal to 0. Right. That should be nice. And then you can even just round off the value of the list that you're using. So 6 decimal places is good. Yeah. So now it looks real nice. So again, the last value of the Romberg triangle that we have here is the correct value of the integral with the least amount of error, and it did 7 whole steps instead of whatever n log 2 is steps. So okay, good stuff.